All right, so we'll get started here in just a moment. Welcome everybody to the Physics Informed Machine Learning Seminar Series, virtual seminars from University of Washington, the Wisconsin-Brenton Group. We are very happy to welcome this week Samy Wu Fung from Colorado School of Mines. Unfortunately, we were scheduled to have Professor Stanley Osher, but he had an emergency. So we were fortunate enough to have his co-author step up and present the work that Stan Osher was going to present. So Samy is an assistant professor, Colorado School of Mines. He graduated from Emory in 2019 and has been publishing a lot of great work on optimization, machine learning, and applied math methods applied towards machine learning. So he'll be talking about the same topic, Hamilton-Jacobi based formula from their recent paper. So I will go ahead and hand it over to Samy. Thank you very much.
All right. Thanks for the introduction, Zachary. And yeah, happy to be here. Thanks for having me. So what I'll talk about today is a work that we've recently been doing with Stanley Osher and Howard Heaton. And yeah, I'm hoping this talk is self-contained, so feel free to stop me anytime if you have any questions. But yeah, let's jump right in. It's essentially on using Hamilton-Jacobi PDEs to estimate proximal operators in general and to solve global optimization problems or optimize non-convex functions globally. Okay, so here's the gang. Thanks, and our sponsors. So very thankful for their collaboration and support. But let's just go ahead and jump right in. Again, I'm not going to assume any background necessarily. I'm trying to keep this as self-contained as possible, but do feel free to stop me and ask me any questions. So we'll start with just some background on proximal operators and proximal methods. So what is a proximal operator? Again, it's part of the title. So let's assume that we have a function that is continuous. In general, we will be interested in minimizing this. So you can even think of this as it could still be, let's say, bounded from below, but to compute a proximal, you don't necessarily need the function to be bounded below. So then you have a function, and the proximal operator is defined as follows. So you give me some positive parameter t, and the proximal operator of f is defined as the argmin of f plus some quadratic term. So it is called a proximal operator because you have a proximity term over here. So if the proximal at x tries to minimize f of z, so it tries to minimize that f, but at the same time, it tries to stay as close as possible to my current variable x. And t here is going to be this parameter that's going to weigh how much importance I give to f or to this quadratic term over here. Again, t small means that I want to be really close to x. T large means that I want to minimize this f. And this shows up a lot in optimization algorithms. I'll give some examples. Okay, so this is just a proximal operator. And I'm going to another term that is sort of an ingredient that is very closely related to the proximal is the Moreau envelope. So the Moreau envelope, rather than being the argmin of this sort of objective, it is the min. So it is the actual min. So to evaluate the Moreau envelope at x, I need to solve an optimization problem or get the props and then just plug it back in here. And I will talk about this later on. But essentially, this Moreau envelope kind of convexifies and smooths out your underlying f of z. And there's connections with PDEs here that will help out. I see something in the chat. Okay. So I'll tell you a little bit about why these terms are important. Let me just set up a little bit more background first. But it turns out that this proximal operator and this u are closely related to one another. And in particular, the gradient of this Moreau envelope u can be obtained in terms of the proximal, and similarly, and vice versa. So if you have the proximal, you can get the gradient of the Moreau envelope, and if you have the gradient of the Moreau envelope, you can get the proximal. Okay. I will give a little bit more intuition about what this U looks like typically. Again, it should be a convexified and smoothed out version of your original function f. And this will be the second part of this talk. But for now, I'm just introducing what this proximal operator is. And it appears in a lot of first-order optimization algorithms, essentially. If you think about a lot of these first-order methods like primal dual hybrid gradient, ADMM, Douglas-Rashford splitting, and in general, a lot of operator splitting algorithms use these proximal terms. Okay, but there is a problem. These algorithms, these proximals, can typically be used in very, very special cases. So note that if my goal is to minimize f, computing the proximal is equally as difficult as minimizing f itself. And so what we want to do is, or in general, this proximal and this Moreau envelope are impractical to compute. Okay, so this is something that we will keep in mind, and really the reason for today's talk. We want to be able to compute proximals for very general functions, f. Okay, so let's just look at some examples about what these proximal operators look like, and and I'll also talk about these Moreau envelopes later on. So for instance, the most straightforward algorithm is the proximal point algorithm. So if I am trying to minimize some function f of x, it turns out that under some conditions, I can just iterate the proximal like this. So for some fixed t, I can just say xk plus 1 is just a proximal of xk for some parameter t. And this is guaranteed to converge to a minimizer of f, essentially. Now, what this means is this algorithm over here turns out is equivalent to doing backward Euler on the continuous on this gradient flow equation. So if I have this dynamical system and I want to flow in the negative gradient direction, if I were to apply gradient descent, then if I were to discretize this with forward Euler, then I end up getting gradient descent. But if I were to discretize this with backward Euler, then it turns out that I end up with the proximal point algorithm. So as everyone probably already knows, backward Euler is much more stable, but much more computationally taxing to compute. So this proximal point algorithm is generally not that useful. Now, a setting where proximal methods or proximal operators show up more is in the case where maybe you want to minimize sum of two functions, f of x plus g of x, where f is smooth but non-proximable. Non-proximal means that there's no analytic formula for f, for the proximal of f, but where g has an analytic proximal formula. So for instance, when g is the L1 norm, this is a classic lasso problem. And for this lasso problem, g has an analytic proximal formula given by the shrink operator. And so in particular, I can apply an iteration that looks like this. So for instance, I can have like xk, I can apply gradient descent on the function f, and then apply a proximal with respect to g. And so this here is called proximal gradient descent. When g is the L1 norm, this is literally the iterative soft thresholding algorithm, or ISTA, which is very commonly used for lasso. Yeah, so another such example is the alternating direction method of multipliers, which can be written in terms of these proxies over here, and then you do some sort of gradient ascent on the dual variable. I'm not going to get too much into this, but this slide is really to show that there are a lot of algorithms that can these proximals appear everywhere essentially, or appear in many places. But the only time that you can truly use them is in the setting where you can either have an analytic formula or you have to employ an iterative algorithm itself just to compute a proximal, which makes them quite computationally taxing. So again, the point of this slide is really to say that these proximals are ubiquitous, but they are impractical to compute for general functions f. And that's the reason why I'm giving this talk today, or the reason for our work. Okay, so hopefully up until now, we've seen that, if I can compute proximals, then I have a lot of flexibility on how to optimize these functions. And so our goal now is to see how we can approximate these proximals efficiently for general functions f. So the way to do this is through some nice connection with, or our way to do this is through some nice connections that we found with Hamilton-Jacobi PDEs. And the idea is as follows. So let's just recall again that the proximal and the Moreau envelope are related to one another. And in particular, the proximal can be written as this sort of affine transformation on the gradient of the Moreau envelope. I recall the Moreau envelope is just the inf, the proximal is the arc min, which again is impractical or intractable to compute for general F. So if we can find some way to quickly compute this gradient of the Moreau envelope, then we have a way to, again, tractably and quickly compute this proximal. So the first observation is as follows. It turns out that this U, this Moreau envelope for T, turns out that it is a viscosity solution to Berger's Hamilton-Jacobi equation. So what does this mean? It means that this U of xt satisfies this Hamilton-Jacobi equation, where D here is a gradient operator. And F here, F, the function that you're trying to compute the Moreau envelope of, is the initial condition. So in fact, it turns out that T acts as a smoothing parameter of sorts, where at time 0, the Moreau envelope is literally F itself. And at time infinity, the Moreau envelope is some flat line that has been diffused over time. Okay, so that's sort of the intuition behind this. Now, this doesn't quite help us to compute the proximal yet, but it does show us a nice connection. So this envelope U is a special case of a class of formulas called the Hoflachs formula that exists for Hamilton-Jacobi PDEs. So this is a particular, a special case of Hamilton-Jacobi PDE. But this doesn't help us quite yet, because if I want to compute this proximal, I still need to solve this Hamilton-Jacobi PDE if I were to do it through this PDE route. And solving this Hamilton-Jacobi PDE is generally quite difficult to do, especially for dimensions higher than 3, where you have to discretize over a grid, for instance. But this is a nice connection nonetheless. Okay, so this is the first observation, that it turns out that this gradient of the Moreau envelope, the Moreau envelope itself is a solution to this Hamilton-Jacobi PDE. Doesn't help us quite yet. So we need some additional observations that we make. And again, because this PDE is tough to solve, what we're going to do is the following. We're going to consider the same PDE, but we're going to add just a little bit of diffusion. So I'm going to add a delta times the Laplace of U in here. And that's precisely what we do here. So instead, I'm going to consider the viscous Hamilton-Jacobi PDE. And in this case, it's exactly the same as we had before, except now I have added a little bit of a diffusion on the right-hand side here. And this PDE, it was proven by Crandall-Lyon, some pioneering classical result that tells us that U delta will converge to the true solution as delta goes to 0, and will converge uniformly. So why do we consider this PDE instead? Well, it turns out that this PDE, we can use a change of variables. We can use a change of variables to transform this PDE into the heat equation, it turns out. And so this gives us an analytic formula for the solution of this PDE over here, which again is a close approximation of the U of the actual Moreau envelope that we're looking for. Okay, so the first thing we do is we're going to consider a change of variables to show you how to actually get this analytic formula. We're going to consider a change of variables, V delta, where V delta is the following. I'm just going to do take an exponential of negative U delta over delta. And this is called the Kohlhoff transformation. And it turns out that if I were to make this change of variables, and I get V, if I isolate U delta here, so if I take logs of both sides, multiply by -1, multiply by delta, so that I isolate U delta, and if I were to plug it all back in here into this PDE, and I rewrite this PDE in terms of V delta, I end up getting the heat equation, it turns out. And this is nice because we know exactly what the solution to the heat equation is. It's given with a fundamental solution here. It's just a convolution. So, so the first idea is to do this change of variables. Once we have this change of variables, we can get the heat equation, and we can get an analytic solution for V delta through this fundamental solution. Okay, so just to back up a little bit, our goal is ultimately to get u and the gradient of u so that I can compute this proximal operator. Yeah, Alan, I think you have a question. Am I supposed to unmute Alan? Let's see.
Sorry, I'll take care of that.
Yeah.
Alan. We will allow you to.
No, I'll jump in. We haven't thought about boundary regions yet, but it's doable.
Yeah, so Keith asked, I'll answer this other question that Stan just sort of jumped in on. So what if the optimization is problems over a bounded domain? So you can potentially include these bounded, these constraints as indicator functions,
Exactly.
and still try to compute these proximals essentially. So it is possible.
Alan is unmuted now too, so you can ask a question if you like, Alan.
Okay.
Oh, great. Yeah, I was just wondering if you can maybe comment on recovering the weak solutions of burgers from this, because yeah, I'm sort of, it's not totally clear to me if you're just talking about strong solutions of the PDE, and yeah, exactly how that interplays with your end goal, trying to compute the prox.
Yeah, so we're just going to, we're going to obtain the viscosity solution to this PDE over here, or an approximate solution. So we're never really going to recover the true U. Instead, we're going to approximate this U delta. I don't know if that answers your question exactly, Alan.
Moreover, now we can approximate almost any convex Hamiltonian this way. I'll jump in.
Yeah, thanks, Dan.
Thanks, and I'll let Alan respond if he wants to. Otherwise, we can move on.
Yeah, I think you answered it. But basically, I'm wondering if you can also like recover. I mean, so burgers generically gives you some solutions that can have shocks, and it's sort of unclear to me what role those weak solutions play in this.
Well, this is a Hamilton-Jacobi equation, so it has it has discontinuities and derivatives, and we get them. This gives you the limit, which is the viscosity solution.
Yeah, it's a smooth approximation in some sense, yeah.
So it's a regular, it will regularize those shocks.
That's
Cool.
right.
Okay,
That's right.
thank you.
Not shocks, kinks, actually.
Thanks,
Yes,
yeah.
okay, yes.
Yeah, cool. I will just move on, but yeah, feel free to ask any more questions. But yeah, we are just going to approximate this U delta, which is again a smooth approximation of this, or regularized approximation, as Zachary said, of this of the solution to the actual Burgers equation. Okay, so just moving on here. Yeah, thanks for the questions. So again, we want to get the solution U delta, and it turns out that if I do a change of variables, I get this heat equation. I have an analytic formula for the heat equation. I'm going to go to the next one. So again, I use this change of variables. Then I can get an analytic expression for the solution of V delta, which is given like this. And this here is really just a convolution where phi here is the a heat kernel, essentially. So I'm going to convolve the heat kernel with the initial condition. And that's a solution to my V delta. Now, why is this useful? It's because I can now rewrite U delta using this expression over here. That's what it is. So doing this, I change my variables. I use a fundamental solution of the heat equation. I do a reverse change of variables now. So I'm going to reverse this change of variables, and I can write the solution to U delta using this convolution here. So it's going to be a negative delta log of this, convolution and so on. So this gives us a sort of an analytic, an explicit formula for approximating this U delta, in fact, and it's done through this convolution. Okay, so again, this is done by the first using the fact that there was a Hofstadter's formula for the Moreau envelope, and second, the Kohlhoff transformation, which allows us to do this change of variables, and then we employ the fundamental solution of the heat equation. And so then the goal is the following. I have this U delta. Now I have this U delta, which is written in this form as a convolution. I have it sort of explicitly, and now my goal is to recall that what I am interested in is not exactly U delta, but rather the gradient of U. Not exactly U, but rather the gradient of U. So I can actually differentiate this with respect to X and get again an analytic formula or an explicit formula for the gradient of u. So it's gradient, and I'm going to assume that for delta sufficiently small, this is going to be a good approximation, and I'll talk more about this. But essentially, I can now approximate the gradient of the solution to the Hamilton-Jacobi PDE or the gradient to the Moreau envelope using this approximate gradient, this gradient of the approximate solution of the Hamilton-Jacobi PDE. And essentially, if I differentiate this with respect to x, it ends up being this quotient here. So I just have to differentiate v delta over gradient of v delta over v delta. So again, v delta being the solution to the heat equation that we saw.
Just to remark, that's the score, would you believe, of v delta up to minus delta.
Mm-hmm. Yeah. So
the score is a very trendy topic in machine learning these days, and this pops up right here.
Right. So there are some connections between this solution and the score function that appears in stable diffusion. Cool. Yeah. Thanks for the comment, Sam. But I'll just sort of come back real quick. So again, if I have the gradient of the Moreau envelope, I have access to the proximal operator because all I have to do now is just do it's just some affine transformation. And so now, once I have this approximation of this gradient of the Moreau envelope, I can now write my proximal in terms of these convolutions. So if I do some algebra, I can pretty much rewrite these convolutions in terms of expectations, where I sample from Gaussian distribution. So it turns out that if I now, this gradient v delta is precisely this part up here, and this v delta is precisely this part down here. And this p x delta is precisely a Gaussian that is centered at x with variance delta t. Okay, so why is this, this part here, you maybe may have some questions about, and therefore you may have some questions about this, but assuming that this holds, then what this means is that now I have a way to approximate the proximal evaluated at x by just sampling, essentially. So it gives us a Monte Carlo approach. It's Monte Carlo sampling where I sample from a Gaussian. That's pretty easy. And all I need to do is evaluate f a bunch of times, pretty much. And so what this tells us is that now I can approximate this prox, but we don't need to discretize. We don't need to use grids to evaluate this integral or to solve the Hamilton-Jacobi PDE, essentially. And this allows us to approximate these proximal operators in higher dimensions, ultimately. Cool. So this is pretty much the punchline, or the punchline of this talk. This formula over here. So as a result, we have a theorem that shows us that, yeah, indeed, if I now take delta and I start shrinking it and taking it to 0, then it turns out that this formula indeed converges to the proximal operator under some assumptions. So what are the assumptions that we have in this case? We require that either f is L-smooth. L-smooth in this case just means that the gradients are Lipschitz continuous, or either L-smooth or f itself is both L-Lipschitz and rho weakly convex. So either of these conditions, if either of these conditions hold, and I choose this t, this smoothing parameter between 0 and 1 over rho, so then it turns out that the proximal is unique because the objective function that this proximal tries to minimize is, or this objective function inside of the proximal ends up being strongly convex in this case. Disregard this part, actually, this part is a bit of a typo, but essentially, if you have these conditions, then as you take the limit as delta goes to 0 of this quotient of Gaussian convolutions, I converge to the proximal operator. So again, the sort of zooming out from a bird's eye view again, I have a general f for which I may not have an analytic formula for the proximal, and I don't want to solve a potentially highly non-convex optimization problem just to evaluate this proximal. We by sort of going through this route of Hamilton-Jacobi PDEs, we can derive a formula that allows us to approximate this proximal using only samples, by the way, and using Gaussian-based Monte Carlo. So here's a couple of remarks or takeaways. So now we can compute a proximal for general functions f. And in fact, note that all we need is function evaluations. And so these function evaluations might even be potentially noisy. So this whole thing, this approximation of a proximal is done completely in a derivative-free manner as well. And again, one final comment on this slide is that because we have an expectation over Gaussians, it's fairly straightforward to sample, and so there's no need for a grid. So we can actually compute these proximals without having to solve Hamilton-Jacobi PDEs over a grid anymore. Just a final comment. This was for the proximal, but the U delta itself, so this is the gradient of U delta, but U delta itself, I can also compute using only one expectation. Yeah, we can also approximate the Moreau envelope itself using a very similar expectation formula. See, I think there might be something in the chat. Okay, nothing. Cool. So this was the takeaway. Up until now, all right, we have a new way to compute these proximals, I would like to give credit to Jerome Darbon, who has also used this formula in the context of image denoising, and of course this formula also appears in Evans's PDE book for some one-dimensional Burgers equations. Cool. So does this formula work? I mean, that's the next question. See, so there's a question in the chat. So to clarify, the reason getting the prox here for general smooth non-convex problems is because convergence rate to a local minima should be much faster than using BFGS. Okay, Alan, that's a great question. So Alan is essentially asking, why do I care about the proximals? Is it faster than methods like BFGS, for instance? The answer is it depends on your problem. But there are many problems or applications where these proximals are very useful. And in particular, I mean, Stan Osher is here, but in particular, there's solving some of these like optimal transport problems. These primal dual hybrid gradient type algorithms are very, very common and very, very effective. And so you want to use these proximal type algorithms in these sorts of applications. So if BFGS is better for your application, then by all means you should use BFGS. I hope that answers your. Yeah.
I want to chime in. First of all, this is a zero order method. No derivatives of f are used. Notice that. We get a C infinity approximation. B, in our first paper, which we should publicize more, we showed that you can prove under pretty general circumstances that this converges to non-convex optimization. Would you believe? We have some restrictions which aren't really serious. And we did some tests. We should do some more tests, and we seem to beat everything. I say modestly, but more work to be done. But this provides a method that we can prove, if we can actually import it and do it, converges for wide class of non-convex methods, convex optimization, and it's zero order method. Okay.
Yeah.
Sorry about that.
No, all good. Thanks, Stan. Thanks, Stan. I always appreciate the comments.
I have to be the publicist here. Sorry.
Yeah. But just to sort of nail it home, Alan, yeah, if you have a zeroth order method, if you don't have access to gradients, then this approach also helps you. So you can use a proximal based algorithm without needing gradients, which you do need in BFGS. But again, yeah, so it's a little bit of a cop-out answer, but hopefully it answers most of your questions. And yes, as Stan was alluding, it turns out that we can use this for global optimization, also as the title mentioned says. Quick, so cool. So let's look at some experiments. The very first thing we're going to do is something very, very straightforward, sanity check, essentially. There are some functions for which we know the analytic proximal formulas. In particular, if I take f to be the L1 norm, I know that the proximal of this function is just the shrink operator, the soft thresholding operator. And so here's what I'm plotting here is the following. I have f of x, which looks like an absolute value. I have the true Moreau envelope, which I can also compute since I have the analytic proximal formula, which is given here in orange. As you can tell, the Moreau envelope smooths out your function. And then this I will talk about again later on when we talk about global optimization. And this U delta is our approximation using our formula. And in this case, the Moreau envelope, you see that, there's a little bit of randomness. As you can see here, these green lines are a little bit, it zigzags just a little bit, and this is due to the random nature of the problem, right? I mean, we are approximating an expectation with samples after all. But this is just a sanity check. And again, even though we want to approximate the proximal, just checking to see whether the Moreau envelope does well, it gives us an indirect way to see how accurate our proximal is as well. So the true proximal operator itself looks like this. And here we have our proposed Hamilton-Jacobi based proximal, which again, it sort of smooths it out a little bit. Again, the Moreau envelope is a good way to visualize how accurate this proximal approximation is, and vice versa. And again, this is only in 1D, so there's no, no surprise here. Now, what we want to do is let's see how well it does in higher dimensions, and so and how many samples I need, and that kind of thing, and how large should delta be. So on the left here, let's forget about the right image for a second. On the left here, all I'm doing is, again, I have this analytic formula for the proximal of the L1 norm, and I'm going to try this for different dimensions. So each of these lines indicates different dimensions. And as you can see, blue line is 10 dimensions. As you increase the dimensions, the accuracy goes down. The error goes up essentially, which is expected. But 10 to the minus 2 is not bad for a dimension 100 approximation. And here in the x-axis, what we see is the number of samples. So clearly, we see that more samples means better because we are approximating this expectation more accurately. Okay, so this is just the approximation of the analytic proximal across different dimensions and number of samples. And in fact, one thing that's quite nice about this formula is that we don't need access to the actual function f, as Stan said. We only need access to function evaluations. So you can give me a very noisy absolute value of f, which can look something like this. And because I only need function values in my approximation of this Moreau envelope, I can, we can still approximate the Moreau envelope. And here we show the Moreau envelope, or our approximate Moreau envelope, for two different values of delta. So here for delta equals 10 to the minus 1, and delta 2 is 10 to the minus 2. So delta 2 is much sharper. And what we see is that the larger the delta, the more smooth is our Moreau envelope approximation, which makes sense because this delta corresponds to the diffusion coefficient of our Hamilton-Jacobi, of our viscous Hamilton-Jacobi PDE. So larger delta leads to more smoothness, and more samples leads to more accuracy. And the nice thing about this figure on the right here is that we do not need access to the true function f, but rather its evaluations, which may be noisy. Cool. So this is sort of a toy problem, sanity check of sorts. Okay, I think Mo has a question. I'll go ahead and unmute him.
Hi, I just had a pretty quick question in terms of clarifying what error you're showing. Is that the error of between the minimizer and what you found, or the error between the envelope and the true envelope?
Yeah, that's a great point. So over here on the left, I'm showing the error between the true shrink operator and the approximate shrink operator.
I see.
Yeah.
Okay, thank you.
Yeah, thank you. All right. Let's see here if there's no more questions. Thanks for the questions, by the way. So let's actually put. So this is this only shows us how accurate it is to approximate the proximal evaluated at one point, or just the proximal itself. So how does it do in action? So how, if I want to now employ this approximate proximal, this Hamilton-Jacobi based proximal, and I want to embed it into an optimization algorithm, the question now is how well does it do? So here we have the ISTA algorithm, which is proximal gradient descent, where the proximal is essentially the shrink operator. And here what we show is how well does it do with the true ISTA. So on the left, all I'm doing is I'm going to fix the number of samples to be 1,000. This is also a 1,000 dimensional problem, by the way. And all I'm going to do is I'm going to vary the smoothing parameter delta. So I'm going to zoom in a little bit here. And what we see is that if delta is, first of all, we do comparatively well to the true ISTA, essentially. So if I were to apply the proximal gradient descent with the true proximal, you get this orange line over here. And what we see is that HJ ISTA, this Hamilton-Jacobi based proximal approach, also does comparably well. And in particular, if delta is too small, you get more noisy approximations, which also makes sense because again, delta smooths out the approximation of the proximal. Okay, so once we do this experiment over here, which seems like, okay, it works about as well as ISTA, we're going to pick the best delta. In this case, it happens to be delta equals to 1, I believe. And we're going to now vary the number of samples. Whoops, sorry about that. And if I now vary the number of samples, this is what we see. So the true ISTA is, again, in this orange over here. In the x-axis, we have the number of samples. In the y-axis, we have the function value. And we see again that for a fixed delta 1, we see that the more samples we use, generally the more accurate. Here, for instance, 100 samples, does worse. We also show gradient descent on the non-regularized term, just as a sanity check to make sure that the proximal is indeed doing something. Otherwise, if the gradient descent does equally as well as everything, then we are not really approximating anything when approximating the proximal. Cool. So Ryan asked a question, and he says, if I may be missing something, but would the equivalent of preconditioning this method be accomplished by choosing a non-diagonal covariance for the noise you sample? Ryan, I think you are correct. You could potentially precondition this. This would be equivalent to doing a proximal with a diagonal weighted matrix rather than a Euclidean metric. You have a weighted Euclidean metric.
Yep.
Yeah. I hope that answers your question, Brian. So there's ways to do it. Okay, let's see. Cool. So again, HA-prox can also be used. All right. So up until now, we've done sort of examples where we can already solve without having to use this Hamilton-Jacobi based proximal. So this HJ-prox is actually more interesting to use in cases where I don't know how to compute the proximal. And that's precisely what we will do in our next example. We're going to consider the following problem. So suppose I want to minimize some black box function. I don't know what it is, subject to some constraints, AX equals to B. And O, for us, the way that we build this O is it's going to be some black box oracle function that is given by this 1 plus epsilon times some random matrix W, some matrix W times X, just to correlate all the elements so that it's not just an L1 norm. And this noise is going to be some Gaussian noise. And yeah, so this would be akin to a zeroth order optimization problem, by the way, because suppose I only have access to function evaluations of O of X. And to our knowledge, we don't know of many algorithms out there, although I may be wrong. We don't know of many algorithms that can actually solve this problem, especially when there are constraints like this, AX equals to B. Typically, the zero order algorithms are based on finite differencing type of approximations of a gradient and so on. So this makes it quite exciting to solve this kind of problems. And because our Hamilton-Jacobi based proximal only requires function samples or function evaluations, we can indeed, in fact, compute the proximal of O directly. And so in this particular setting, if you have the proximal of O, one trivial or one sort of straightforward method is the method of multipliers. So I'm just going to apply the method of multipliers to solve this constraint optimization and assume or pretend I had O explicitly, essentially. Cool, so that's what we do. And in here, what we show is precisely the same experimental setup as we had for HJ-ISTA, where on the left side, I'm going to fix the number of samples to be 10,000, and I'm going to vary the smoothing parameter. And what we see here is that, I'm going to zoom in a little bit, what we see here is that they do fairly well, but as you increase delta, typically you get the smoothness is helping us a little bit. Up until about delta equals to 10, we do better. But then once we bump it up to 100, then we over smooth, and our method of multipliers doesn't do as well anymore. By the way, this error is computed by assuming, let me go back for a second, by first solving the problem with a non-noisy version using ADMM. So I'm going to numerically get this, I'm going to get this numerical true solution by solving the non-noisy problem. And then that's what I use here for the relative error. And on the right side, I'm going to now fix that best delta, which is delta equals to 10, and I'm going to vary the number of samples. And what we see here is that if I use one sample, it diverges because I am nowhere near an accurate approximation of this proximal. But as I increase the number of samples, I do better and better. And in particular, we use up to 10,000 samples. This is a 1,000 dimensional problem. So 10,000 samples is actually not bad, depending on your application. And again, we do gradient descent just as a sanity check that our proximal is indeed doing something. So again, we numerically compute the true solution or the solution to the non-noisy oracle and treat it as a quote unquote true solution. And what we are observing here is that in fact, we can, the different settings give us HJprox embedded into this method of multipliers is indeed fairly effective. So anyway, this experiment here is, I think, is quite nice because again, we were not aware of too many methods, and again, I may be wrong, that can solve this problem here, where you have a zeroth order sort of black box oracle, but you have also some constraints in there as well. So that concludes the first part of the talk. The second part is much shorter as well, but this is for approximating proximals using this expectation formula. That's all it is. And we show you some experiments. We prove that the limit as delta equals to 0 converges to a true proximal, and perhaps more importantly, we are able to use this on black box functions that may potentially be noisy.
Very quickly, the preconditioning question was interesting, and it's equivalent to solving a different Hamilton-Jacobi equation using Hopf-Lax formula, which we have done, but not in generality, but we have. It's a very good question, and it's useful.
Yeah, so that's the nice thing where preconditioning ties in with solving a slightly different Hamilton-Jacobi PDE.
But still convex.
Yeah.
And in fact, we can use any convex, I'm not saying any, but reasonable convex functions instead of x minus x squared, xk squared.
Yeah.
Okay.
Cool. Thanks. Thanks for the comments, Stan. So I'm just gonna, for the sake of time, I'm gonna move to global optimization now, which also may be of interest to most people here. So now my goal is, besides just computing proximals, which can be used in all these first order optimization algorithms, I now want to compute, minimize this f itself. And I'm going to assume that f is continuous and bounded below. And I'm going to just quickly recall this definition of the Moreau envelope, where it's the minimum of this f plus this proximity term. And I want to very, very quickly, let me just, so t here, it turns out, is a smoothing parameter, as you might have already seen from this Hamilton-Jacobi connection. But note that if t equals to 0, then pretty much, or is very close to 0, then pretty much the solution to this minimum minimizer is z equals to x, because the weight of this whole thing is, all the weight is going to this quadratic term. So I just need to minimize this quadratic term. So essentially the Moreau envelope evaluated at x is x, essentially, if t is near 0. Sorry, it's f of x, because now once I solve it for the minimizer being z equals to x, I plug it back in and I get f of x back. And if t equals to infinity, it turns out that the Moreau envelope is going to be a flat line at the minimizer of f, because if t equals to infinity, this quadratic term goes away, and you're pretty much just getting the minimum value of f for any x. So you just get a flat line at the that touches the global minimum of f. So essentially, t equals infinity is smoothing it out all the way onto a flat line. T equals 0, you recover the original f itself, and that sort of coincides with the theory of Hamilton-Jacobi PDEs.
In between, you get parabolic type things, which eventually flatten out to the minimizer.
That's right. So then what Stan is alluding to here, or stating here, is that what we want is pick some large enough t such that this function, this f, gets smoothed out and convexified as well. And so if I pick t large enough such that it is not completely flat, but yet convex enough, then I can get access to potentially finding global minima of f itself. And it turns out that the answer is yes. If for large enough t, you can minimize the Moreau envelope, and that gives you a global minimum of f is a punchline. So just to give you sort of an idea of what this Moreau envelope looks like, imagine you have some highly non-convex function f that looks like this. And if I pick the Moreau envelope, if I now plot the Moreau envelope at every point, and I pick a large enough t, it turns out that the Moreau envelope might look something like this, somewhere in between t equals 0 and t equals infinity. And this is nice because this means that, I mean, I would much rather minimize this orange line rather than the blue line, essentially. And I can sort of roll the ball all the way down to this global minimizer. So this is a nice thing because we now have, note that we now have a tractable approximation of the Moreau envelope and its gradient, which means that we can just do gradient descent on the Moreau envelope for large enough t using our formula for the proximal. And that's essentially what we do here. And it turns out that under certain assumptions, the global minimizers of f coincide with local minimizers of u. And under some fairly mild assumptions on f. Essentially, you need f to be continuous, and you need f to have the set of global minimizers of f to be compact. That's pretty much all you need, and you can guarantee this sort of thing. So what we can do is, if we want to find the global minimum of f using our proximal formula, we can just perform gradient descent on the Moreau envelope. If we just pick a large enough t so that this sort of so that we get to the global minimizer. So this slide here pretty much tells you the entire idea of using our formula in the context of just minimizing the Moreau envelope. Cool. So in the context for the sake of time, so here's what it might look like. We called it HJ Moreau adaptive descent in our paper, although we don't need for any adaptivity, we found out later. But essentially, you pick a large enough t, and let's say that I start here, and it turns out that if I perform gradient descent on the Moreau envelope, I can just sort of get to the global minimizer of my function f. And so again, the idea of this approach is to use the same trick, the same sort of approach, the Hopf-Lax formula, and then use a Kohoff transformation to get an approximation of this gradient of the Moreau envelope. Cool. So just as a quick illustration, let's suppose that I have an f that looks, this Green-Wong function, which is highly non-convex. And we're going to perform gradient. We're going to start far away from the global minimizer, which happens at 0. And I'm going to use gradient descent, and I'm going to use our proposed approach. And so forget about, let me just zoom in on the right side here. So the global minimum is in the middle here in red. The initial point is in the black X over here. If I perform gradient descent, I converge to the nearest local minimum. If I use our proposed approach with the Hamilton-Jacobi based gradient of the Moreau envelope, we can converge to the global minimum. And so what we see here is that the objective function values goes down for both of them, but because HJ mad in our case goes to a global minimizer, we converge. But perhaps more illuminating is this gradient descent with the relative error with respect to the true solution. And the gradient descent error, relative error goes up because you move away from the true solution in this case. Cool. Just as a final sort of experiment, so we compared this. We went to, I believe, let's see, what is it? I think SciPy. We just got some Blackbox global minimization algorithms, most of which are based on heuristics. And what we are plotting here, so this is our approach: pure random search, differential evolution, Bayesian hopping, annealing. And what we're showing here are function evaluations. So what we have here is that pure random search takes 460,000 for this function evaluations to converge, and so on. And where there's an n, it means that the algorithm did not converge. And wherever there's a parenthesis, it means that we're using gradients on top of the function evaluations. So what we see is that it shows some promising results on sort of these benchmark problems, albeit these are lower dimensional problems, but we seem to do pretty well in terms of convergence and function evaluations. But again, do note that this is a stochastic algorithm, so you need not expect very, very high accuracy. Cool. So just to sort of conclude here, what we've done is really use this route of Hamilton-Jacobi PDEs to come up with formulas to tractably compute the proximal operator and the gradient of the Moreau envelope. And this allows us, for the proximal, it allows us to solve these sort of black box, potentially noisy zero order noisy optimization algorithms. And we saw that it converged comparably to these to existing optimization algorithms as well. We can solve these zero order algorithms where you have these constraints as well, and it seems to be fairly promising in minimizing non-convex functions as well. Of course, it all sort of hinges on how accurately you approximate these expectations. And so, yeah, so small footnote there. Yeah, our work was recently accepted to PNAS, but also the work on global optimization was also accepted at this Communications of Applied Math. Thank you all for your attention.
Keith, you're right.
Yes, yes, Keith, you can use it for backward Euler.
That's exactly what we are doing, as a matter of fact.
Yes, let me just go back to the very first, yeah, very first slide. So to answer Keith's question, who asks whether this is an algorithm to effectively implement backward Euler, the answer is yes, because again, the proximal of f is precisely a backward Euler discretization on the gradient flow of f. So thanks, Keith.
On the other hand, the error is O of delta, which might not be.
That's right.
Yeah, but you could do it without grids and everything.
So I'm going to answer Michael's question first. So the question was, if our trait study was on number of iterations, did you also compare computational time? So Michael, we actually compared it not with respect to, oh, I think you mean, let me just go very quickly to the, so Michael, if you're referring to these experiments here, yeah, we only compare with respect to iterations. With respect to time, we didn't really compare those. It's up to, it depends on how you, oh, I see, second to last slide. So just to go to Michael's question. So Michael was referring to this. So here we are comparing with respect to function evaluation. I'm assuming that function evaluations is my currency. So we didn't do a time check, but I assume that function evaluation is fairly agnostic and impartial in terms of comparing these. So we didn't compare iterations, Michael. We compared function evaluations. I hope that answers your question. So let me just go through, I think Mohammed had a question. So backward Euler only for gradient flows. Backward Euler for anything, I guess.
Of course, why not?
Yeah, but you would need to be able to evaluate this f, Mohammed. So it's a gradient flow because we had gradient of f, but to compute this proximal, I need to evaluate f. So you need to have some sort of gradient in there, I would say. I'm going to just quickly answer Alan's comment, which is, can you comment a bit more on the limitations of the global minimization? Presumably, there are very non-convex problems that will require very heavy computation, even with a Moreau envelope. Yes, so to answer Alan's question, note that the gradient of the Moreau envelope for us is given precisely by this, this formula over here.
For function.
So here, so Alan, the limitation comes down to how accurately you can approximate this expectation. You can, and there are ways to, you can do importance sampling potentially, but there are ways to potentially remedy it in some ways. So it's not a one-all be-all type of approach, I would say, but definitely the limitation lies on how accurately you can approximate this.
We have some limitations on F also, which are not onerous. Basically, you can't have an accumulation point near the minimizer. You can't be flat, for example.
Right. Oh, yeah, that's a great point, Stan. Thanks for bringing that up. So another answer to Alan's question, if you have, for instance, sine of x, if you're trying to minimize sine of x, the Moreau envelope is completely flat, which means that you can make absolutely zero progress when you take the gradient of the Moreau envelope. So that's also one limitation.
But if you cut it off, if you multiply sine by a characteristic function, it works.
Yeah.
Great talk. I'll abuse my privilege here as the host to ask some questions. You have your smoothing parameter delta, and you choose it appropriately to make your function have the right sort of scale. So I'm curious, in applications where your objective function has very ragged, differing scales and differing parts of your domain, is a single smoothing parameter going to be possible, or can you have an adaptive delta that varies over your domain?
That is an excellent point. I haven't fully thought about it, but I could imagine you doing some sort of domain decomposition and then applying these sorts of schemes in different parts of the domain. So yeah, I would say that you probably would want this delta to vary in these different parts of the domain where the function is, very oscillatory over here, but maybe fairly flat over here, so you don't need to smooth so much and so on. Yeah, thanks for the comment, Zachary.
Yeah, yeah.
Better yet, how about preconditioning as was suggested, which I really like.
Yeah, very interesting work. Thank you so much. Okay, let's see if there's any more questions.
I'm not sure if Mohammed has another question. I see the hand raised. But...
Yeah, let's allow him to unmute himself and he can ask a question.
All right, thank you. Yeah, I had one more question. So this formula that you have, 14, because it has sampling in it, I expected that you need a lot of function evaluations, but actually your 23rd slide shows that no, you don't need onerous number of function evaluations. So could you comment on that?
Yeah, the key.
So well with so
yes.
few function evaluation.
Yeah, so the key trick here lies in the variance, right? So the variance is delta times t. So you can either choose a smaller time or shrink the delta potentially at the risk of numerical instabilities because you are taking e to the minus f over delta.
Oh, I see,
so there's some sort of trade-off going on. Yeah. So you can sort of
Okay.
potentially find a delta where you don't need so many samples, so you can have something that's closer to a delta function.
Beautiful.
Direct delta
Perfect.
function.
Thank you.
Yeah.
I can't help myself. I got to say, this stuff generalizes. We did it for the WSINDy proximal, if anybody cares about that. And we get a nice formula, which is computable. Moreover, we can replace Cole-Hoff by something completely different, which allows us to generalize this like crazy, which is coming up very soon. And finally, this just appeared in the Proceedings of the National Academy of Science, if you want to see it.
Awesome. Thanks, Stan. Everybody check out the paper, please. And thanks, Samy, for the really great talk and the great work. I guess if there are no more questions here, we will wrap it up. Thanks so much to everybody. And we will send out more messages for the next seminar in the following month.
Yep. Thank you, everyone.
Good job, Samy.
Thanks, Stan. Thanks for the cameo.